Whoa. Having a tough time with the autofocus there.
I hate this stupid system.
At least they changed it so pressing down does turn them off instead of just toggling them.
Not sure what they were thinking when they laid that out.
It's like a puzzle.
Walk into the red more environmentally safe.
Yeah, let's go with that.
We use the old dress because they get tired of fiddling.
Yeah, exactly.
So they just turn it
Just
off.
make
and
them
like,
mad,
I'm
so they
fine.
don't
I
even
can
turn
do
on the
homework in the dark.
All right.
Curious.
3 o'clock. I'm time to make any comments. I have to get going. All right. So finishing up chapter 4 today. We've talked everything we've talked about so far are stresses applied by loads. Today, I'm going to add to that what we call thermal stress, which is a little bit of an oxymoron. It's not really a thermal stress. Yes, go ahead.
Quick question, what is the warranty for this?
Whenever it says on the syllabus. I don't keep track of that. Set it up to begin with, and then. So, well, let's see. The stuff that we're finishing, yeah, right. So it'll be one lecture period after. So we always have that one in between. Okay. So thermal stress is a little bit of an oxymoron. It's not actually a stress created thermally. So thermal stress is actually a stress that is a reaction to a change in thermal condition. Okay, it is not thermally applied stress. What is thermally applied, what we actually have, is thermal expansion. So, have you ever talked about thermal expansion yet in any of your classes? Okay, I don't think so, I'm new to this. So, what happens when you heat something up is you get a thermal expansion, a delta, like we've been talking about, a change in length due to thermal conditions. And that's defined by some constant alpha, which is a material property. So there's a thermal expansion coefficient for each material. So I give alpha of aluminum if it's aluminum, of brass if it's brass, and so on. And it's just a number. So typically sort of a 10 to the minus 6 kind of a number. Times delta T, the change in temperature of the material, times L, the initial length of the material. Or you might list that, you might show that as L naught being the temperature before the heat, the temperature, or the length before the temperature change. Okay. So at least to a first approximation, that's it. Alpha is actually, alpha may, true thermal expansion may be a nonlinear function of temperature change, but the nonlinearities are small enough that we can make it a linear function of temperature change. So there may be other alphas for T squared, delta T squared, and so on. Okay, we wanted to get very precise. But for everything we're going to work with, it's just a simple constraint based on temperature. So if I have an object between two solid supports, an aluminum bar between two concrete blocks or something, and I change the temperature, as we talked about before with the concept of superposition, if the second block wasn't there, right, so if it's just this, just a bar sitting out there in space, and I heat it up, it's going to elongate. And the amount that it elongates is delta sub T, thermal expansion. But if I constrain that bar, then by the concept of superposition, there must be a reaction force at that end, which when summed with the thermal expansion gives me a 0 net elongation. So there must be a stress induced in the material by this reaction force in order to cause a net change of 0 in its length. So this is what I'm saying, the thermal stress is actually not applied thermally. This theta P, this delta P, is what's actually stressing the bar. The bar is stressed because there's a load. Okay, there's not a thermal stress, but it's thermally induced because of the constraint. Okay, does that make sense? And so in that case, delta P then is just going to be equal to minus delta sub T. And the easiest way to solve it is to use superposition. Find out what the delta would be for the temperature, and then add back in the stress.
So it doesn't get wider.
Well, it does get wider, but it's unconstrained, so there are no thermal stresses in the lateral dimension. Right, it can expand this way all at once, and there's not going to be any stress induced because there's no constraint.
Okay.
So you only get thermal stress if the bar is constrained, or if the object is constrained. Sometimes it can even constrain itself. Glass, actually, tempered glass. You ever seen tempered glass? You ever see like a car accident when the back window gets shattered and it shatters into a bazillion tiny little pieces? Instead of just breaking and sort of splintering like glass normally would, the back window's tempered glass, or these windows should be tempered glass. If I took, I'm not going to do the demonstration, but if I took a hammer and smacked one of these things, it should go and just fill with a whole maze of cracks. And that happens because it's under a state of residual stress. The inside is being stressed by the outside and vice versa. So one is constraining, it's kind of like an Oreo cookie. Like the chocolate part is constraining the middle, and the middle is constraining the chocolate part. So the constraint can come even from within the sample. So you could have something that's experiencing thermal stress that's just sitting there in space. But something has to constrain it. Okay? Okay. Any other questions? Okay. So it's one concept, just another place you get another delta, but still just another delta in our equations we've been using. Okay, so we'll just still add in the delta and solve it the same way, and we'll do a problem. The second variation is a stress concentration. If I have a sample that looks like this, and I pull on it with a force P, and I know the initial cross-sectional area, I know that the average stress through that thing is just P over A naught. But in the center, there's a hole. Right? So if I showed the thing in full cross-section like this, there would be another hole, hole there on the back. You see what I'm saying? The cross-sectional area here is different than the cross-sectional area there. So the stress here is inherently going to be different than the stress up there. But it turns out the stress here is going to be more than just a change in cross-sectional area. There's actually going to be more concentration than just that. So if I take this thing and slice it in half, and then just look at the bottom half. And now I am going to just look at it in profile, forget the three-dimensional stuff. If I plotted the stress across that end face, right, there's some average stress. If I plotted stress as a function of position, right, there would be some average, let me do the stress actually in red. So I'm going to plot stress as a function of position. The average stress would be that. Right? There's some uniform average stress that I can calculate based on the cross-sectional area up here. A naught. But the actual stress in the membrane is going to look something like this. Okay? In other words, the stress here doesn't just go up because the cross-sectional area has gone down, but the distribution of stress changes. There's a greater stress right here at the edge of the hole than there is out here on the surface. You see that? You understand the drawing? So there's going to be some kind of maximum stress here that is bigger than the average stress here. Okay? So there's something about this hole that causes the stress to go up, and there's a lot of very detailed mathematical analysis that goes into sort of arriving at what that is, how that works. Okay, there's a lot more stuff going on. We'll talk a little bit about it in material science next year, where we talk about the stress concentration factors for cracks. We have a crack in a material, because as it turns out, the degree to which that stress is amplified depends on this radius of curvature r. Right? And in fact, as r decreases, the maximum stress increases. So there's an inverse relationship. It's not a direct inverse relationship, but as r gets smaller, so that you get a smaller and smaller hole, the stress concentration at the edge of that crack goes up. So a small hole has a bigger stress at its surface than a large hole.
Is there like just a really simple explanation for that? Or?
So come back next semester and talk about it in material science. You know, I don't spend too much time talking about it here. Okay. So rather than try to dig into the math behind this, because it's not a nice, easy, clean, exact math, we instead, for the purposes of this class anyway, are just going to define a stress concentration factor. Give it a capital K, and it is just the ratio of that maximum stress to the average applied stress. And this is entirely determined by geometry. So if you look over on the screen over here, there are two ways you can concentrate stress. One is with a hole in the center, which is shown in the right graph there. I don't have a meter stick point. Oh, there it is. So you have this configuration, or you can have fillets on the side. So instead of having a hole, you have a sample that looks like this. So we have these sort of quarter-rounded fillets on the side. And there are several geometrical parameters. There's this dimension here, which is the width of the whole thing, W. Then there's this dimension here, which is H. The section in the center, you know, the narrow section. There's no W and H here, we just have the W up here because there's no narrowing of the width. And then we have R, the radius of curvature of either the hole or the radius of curvature of the fillet. It's the same idea that, you know, so R is still a radius of curvature. And then you can see here on the diagram that the key characteristics we care about are R over H for a fillet, and 2R over a W for the hole. 2R being the diameter of the hole. Okay, so that everything's defined in terms of those things. And as a result, you can kind of see the stress concentration factor. So you think about it, as R gets smaller, right? We're moving from right to left on this graph, and the stress concentration factor goes up. But it's not a linear relationship. Okay. And here, the average stress is defined in terms of the cross-sectional area at the hole. So in other words, they've already taken into account, on the graph, they've already taken into account the reduction of cross-sectional area that resulted from the presence of the hole. Okay, so that piece has already been taken into account. And yet still, there's a concentration greater than 1. Okay. And you notice most of these are 2 for the hole. They're greater, most of them are greater than 2. In the case of the fillet, now we have to have a bunch of different W over H values. So it depends on the relative size of these two, the narrow section and the thick section. If the narrow section and the thick section are very close to each other, you get a very small, a relatively small stress concentration factor. If the narrow section is much smaller than the W, then you get a larger stress concentration factor. Okay, so the bigger the difference in W and H, the more stress concentration you get. Okay? These are just empirical values, at least as far as we're talking about in here. We're going to use these as empirical values. So literally, this table in your book, page 163, I think, in your book, if you've got this year's, if you get the new edition, I can't remember, I don't know what it is in the old edition. But that table is going to be the mechanism by which you calculate your stresses, stress concentration factors. Okay. For the time being, like I said, in a more advanced class, we can talk about it a little bit in material science, and then a little bit more if you ever took a graduate level course in mechanics of materials. Any questions? Okay. There are some things you can do to actually make this better. So there are some things you can do. You can actually kind of remove material out here. Sometimes people drill holes or just kind of etch away some of the material out here on these edges, so that you're effectively making more gradual this W to H transition. So if you look over here, as I say, you get a high stress concentration when there's a big difference between the two. But if you cut those holes out, you're effectively narrowing W, making W smaller, and you're moving to a lower stress concentration factor. So sometimes if you actually had a part like this, you might remove some of this material if you absolutely had to have this kind of short, this sharp round corner in there. Alternatively, the best way to do it is to make this bigger by adopting a geometry that looks something like this. Because now I've made my R much bigger. My radius of curvature is much bigger. And for the much bigger R, I'm moving way out there to the right of the graph, and I've substantially reduced my stress concentration factor. Okay, but if you can't reduce that, then you can at least remove some of the material in here, and it's kind of like the bar doesn't know that that material is there, so it pretends like it's not there. Okay.
That's interesting that you're taking material away to make the bar stronger.
Right, yeah. Because the actual strength of the bar is limited by this.
Right. The smallest.
The smallest dimension, right, right. So that's we're concentrating relative to this dimension. Right? So we're removing material in an area that isn't experiencing the greatest stress, in order to make sure that the region that is experiencing the greatest stress right here has a reduction in stress. Okay.
Yeah. So it's a little counterintuitive, but it makes sense.
Yeah. Okay. What's that?
Maybe not as much as modern physics.
Counterintuitive or
Yeah.
makes sense?
Well, true. Okay.
Yeah. All right.
Right, Jesse?
Yeah. Okay. So, any questions about that do a couple of problems. All right, so let's look at the first one first. Okay, so we have here a red brass rod AB and a 2014 T6 aluminum rod BC that are joined by a collar B. And everything is without load. There's no forces acting when it's at 50 degrees Fahrenheit. But now the whole assembly warms up to 120 degrees Fahrenheit, and we need to find out how much stress that has induced inside the bar. And then we also, once we know that, want to find out how far the collar B will be displaced. Does that make sense? Because one side is going to presumably expand more than the other. So the collar B will not stay where it is, it'll move either to the right or to the left, depending on how much each side expands. So in other words, if the brass expanded significantly and the aluminum didn't, then the bar would move to the collar would move to the right, because the major expansion was happening on the left, even though the whole thing doesn't change length. Okay? Does that make sense to everybody? Don't tell me you're making paper airplane class here. Just making sure. Okay, so what do you want to do first?
Free body diagram?
Free body diagram. When in doubt, throw a free body diagram. Okay, of what?
The whole system, and then maybe we'll split it up into two smaller free body diagrams.
Okay, so we'll do the whole system first. A, B, and C. Okay. What forces do you have acting on A, B, and C?
Well, we can already say that the temperature is 120 degrees Fahrenheit,
Right,
since there's no force at 50 degrees Fahrenheit.
right.
And we can say that there's going to be normal force opposing the expansion of the bar at the end of A.
Okay, so to the right and to the left is that drawing.
To the right, my right,
Right.
and opposite at C.
And then C, going back that way. Okay. So we have force at A and force at C.
Now, if we're making a free body diagram of the whole system, we don't need to do any forces about the collar, right?
Right. There are no forces other than internal forces at the collar anyway. Right, there's no external applied forces. Okay, so first we know one thing from the free body diagram. What's that?
It's
Okay. Maybe you could have something a little more analytical than that. But, what do we know about our forces?
It's a straight line.
It is a straight line. It is indeterminate. But what do we know?
C equals 0.
Right, so we know that FA is equal to FC, because I've drawn the vectors and their orientation, so I don't have to worry about the sign of the forces, right? The magnitude of the forces is equal, and the direction is captured in my free body diagram. So we know FA equals FC. So, no matter how I section this thing, right, because Colin was talking about taking a section, then as another free body diagram, no matter where I section it, I'm going to get an internal force that's equal to that. Right? That is the only force that's present. Right, if I take this section on the right, sum of the forces equals 0, the internal force has to equal FC. If I take this section on the left, sum of the forces, internal force has to equal FA, which is equal to FC. You see what I'm saying? So we really have one force acting.
So then we look at the strain.
So now we have to look at the strain, or in particular, the displacement. Right? So what do we know about delta? do we know about delta? Equals 0, right, it's constrained on both ends, so the total delta equals 0, right? So what deltas are present?
There's delta AB and delta BC. I guess we can assume by the question that one is going to be positive and one's going to be negative. As in one's going to compress and one's going to.
Presumably, but we don't know which is which. So what is delta AB equal to then? Minus delta BC, actually. Yeah. But, I mean, something that's going to get us toward a solution.
Is it the alpha DT09?
I'll call it alpha sub BR for brass. Delta T L naught brass. Is that it? That delta AB? Yes or no?
Yes.
Got three nodding heads over here. Gotta get Ben and Clayton to come in. Is that delta AB? Yeah, and you, Clayton.
I'm trying to figure out whether or not the negative sign comes in on this.
Don't worry about the minus sign right now.
Good on the answer.
Okay. Still not right though.
Yeah,
You're right.
Tricked us.
So if the temperature increases, it's expanding, right? You're talking about the sign. If the temperature increases, it's getting larger. And we said before that expansion or tension is by convention positive. So we know this is going to be positive. Okay. Well, if this is positive, and similarly, delta BC, what's delta BC going to be? If this is delta AB, what would delta BC be?
Well, it would have to be negative, but
But it's not.
that would assume the temperature is getting colder.
All right. So they're both positive values. They can't possibly both be positive values. What are we missing?
We need to,
Positive, negative displacement.
I mean, positive and negative.
we need the strain, that's the stress.
Actually, that's the displacement, so it's the strain that would result from the thermal excitation. It is the elongation that would result from the thermal application of thermal energy. But what are you talking about, the strain?
Deformity.
Right,
It's gonna deform, so B is gonna move.
Right, so there's still a force acting on this, right? We already said that there's going to have to be some kind of force. This thing wants to expand against fixed constraints. There's going to be a reaction force. That reaction force will also cause a displacement, right? If I just had the reaction force, it would cause a displacement in each of these pieces. So if I just took BC, all right, here's my BC, there's F sub C, this is my internal force, also equal to F sub C, right, so this is BC. So there's going to be a delta associated with that force. See it?
Which is the delta that we learned at the beginning.
Here's the delta that we actually talked about, yeah, last time, or whatever it was, last week sometime. Anybody remember the expression we had for that delta? We derived for that delta? We don't have to do any integrals because it's all a uniform bar, everything's the same along the whole thing.
The force over area.
Times the change in length.
Not change in length, it is the change in length. You're looking too early. You gotta look after we did the integration.
Whatever E was, I can't remember.
Where's that going, numerator or denominator?
Denominator. Can't
Right,
remember.
E is the elastic modulus,
Elastic
Young's modulus. All right, one more piece.
The
Actually, it's the initial length, but they don't list the subscript on there because when you integrate dx along the length, you just end up with L. But the assumption here is that L doesn't change significantly as to change, you know what I'm saying? Okay. But you're right, so it's the initial length. That's fine. We'll just leave it as the initial length. They don't differentiate. Once you get into engineering stress, they no longer differentiate initial and final length. Here we're dealing with engineering stress and strain. The length is always the initial length. Okay. So, but the thing is, I need to label that, which length of what? What length has to go in there? BC. The area is the same for everything. Cross-section area of each member is 1.75 square inches, so that's constant. So I can just leave it as A. What's E?
Okay.
No, what, E of what material? Aluminum, right, because the right-hand side is aluminum. Okay. Is that good? Anything else?
You can come up with one for AB.
Yeah, I'm just talking about BC
Oh,
filings. Is there anything else, or are we done? It's compressive, so what does that mean? It means it's negative. Right? Now we're going to come up with one from AB as well. What's it going to be?
FA, or I guess you already put the minus sign in there.
All right.
L, A, B, over A, E, S.
Right. Right, so now we have a mechanical displacement, elongation, and a thermal elongation. And the total elongation of each piece is the sum of those two, superposition. So the total for AB is this minus F, well, since we have FA equals FC, I'm just going to call it F. Right? F LAB over A E brass. And the BC is going to be this minus F LBC over A E of aluminum. We good now?
So we need to put those in when we do our total strain,
Total elongation.
total elongation up there.
Strain is always divided by L naught, so.
Okay, what does delta actually stand for? Is that
Elongation.
Elongation.
Right, so strain is delta divided by L naught. It's the ratio of elongation to the initial length. But here, we don't have this, we don't really have an initial length, right? We could do this one, right? Because this aluminum here, this is also LBC. I should be consistent in my nomenclature. Right, I could divide through here by AB and find out the total strain in AB. But that's not what I'm interested in, because the strain doesn't add. What I can add is the total displacement. Right. So, now I've got these two expressions, I plug them back in up here to get the fact that the sum of these two is equal to 0. You all right with that, Blake? You look at me kind of like,
Yeah.
I'm not convinced, man. All right. So then my total displacement is going to be equal to alpha of brass delta T times length AB minus F times length AB over A times E of brass plus the other piece, alpha of aluminum delta T times length BC minus F times length BC over A E of aluminum. And that whole thing is equal to 0. Now let's go through and see what things we know, what we don't know. We have an expression, make sure we can fill in all the blanks. Do we know alpha of brass?
Is that something we look up?
Probably something to look up.
Look up E.
Yeah, I'm trying to find out what it is. 9.8 times 10 to the minus 6 alpha brass. Do we know delta T?
Yeah.
What's delta T? 70 degrees Fahrenheit, yeah. What's LAB?
Uh,
3 feet, hopefully.
Feet.
We're in English units. Do we know F?
No.
Nope, that's what we're solving for. LAB we already have. Do we know A?
Yeah.
It's-
1.75.
Okay, do we know E?
Look it up.
Look it up. Value of E is 14.6 times 10 to the 6th in SI, or in English units. And then similarly, we look up alpha, and we look up E, and everything else we know. Okay? So then we can rearrange and solve for F, and F is equal to 1,793.4 pounds. Okay, so 17 kips. Okay? So that's my force. Is that the end? Yes or no?
No.
What else do I have to find? Hmm?
Displacement of the collar, right?
Displacement of the collar. How am I going to find displacement of the collar? How am I going to find displacement of the collar? Anybody can answer.
Just the displacement of AB minus displacement of BC.
That would give me 0.
Could you look at the difference of compressive forces in AB and BC? Or the difference of compressive forces in AB and BC, well, aren't those the same? It's the same force,
It's the same force, yeah.
but with reference to their different materials. So how one bar would deform with the same force would be different than how the other bar would deform with the same force.
So that is the motion of B. Right? The elongation of the AB segment is how much B moves. If this is a negative value, that means B moves to the left, because AB got shorter. If it's a positive value, AB got longer, B moved to the right. Right? But this is the elongation of this left-hand segment, which is the motion of B, because A is fixed on the left-hand side.
Okay, and you also, yeah, okay.
If I plug that into this value down here, I would just get a negative of the same thing.
Yeah.
Right? So it's not quite, if you took delta AB minus delta BC, you'd actually end up with 2 times the motion of B. Okay, because this one's negative this. Okay? So if I do that, plug that number back in, using all the other values that we have, we end up with 0.611 times 10 to the minus 3 inches. So, not even a mil, not even a thousandth of an inch. B barely moves, which makes sense, right? We wouldn't expect it to move much.
If that was the same material, it wouldn't move at all, right?
If it was the same material on both sides, it wouldn't move at all.
But they would have to have the same area too.
Right,
The bars have.
right, well, this bar does have the same area, right? You could do the same thing by saying I got a bar on the right that has a smaller cross-sectional area than the one on the left. Then the one on the right would have a greater stress, So it would, now one thing we didn't really do along the way here, that would probably be worth doing, is to find out, once we found our total load, go back and find out what the stress is in each of these two members. So the stress in the brass, right, the actual stress, is the load divided by the cross-sectional area.
Isn't that what we're looking for? Normal stress?
Is it stress? Oh, normal stress in each member. Yeah, you're right. You're right. I take that back. I thought it was the normal load. You're right. So we do have to calculate the stress. So the normal stress is 9.77 KSI. Okay, so that's actually the normal stress. You're right. Okay. Now, but the thing I was going to say is you want to go back and check and make sure that that is less than the yield strength of each of the two pieces, the yield stress. Because if it's more than the yield stress, then it's no longer behaving elastically, right? And so we're actually not going to be able to do this. Right? Because this right here assumes we're in the elastic regime, right? The elastic modulus, that's why we're using Young's modulus. So you have to go back and check the yield strength on those two materials. And for, let's see here, magnesium, aluminum, 2014 T6, the yield strength is, in compression, is 60 KSI. And we're at 9 KSI, so we're 10 KSI. So we're below the yield strength in aluminum. And in brass, where's brass? Red brass. The yield strength in red brass is 11.4 KSI. So we're much closer there, but it has not yet yielded.
So would this probably be in the stage where it's deformed, but it hasn't gone past the...
Right, it's still in the proportional range. So it's an elastic deformation. It's squeezed, but if I cool it down, it'll go back to the way it was. But if this number were 12 KSI, then when I cooled it off, it would shrink back, try to shrink back beyond what its original dimensions were. Because I would have compacted it, it would have yielded, it would have had some kind of compression and corresponding probably bulge. See what I'm saying?
Yeah.
So if this was above the yield strength, if this was 12 KSI, then I would have squeezed it, it would have been compacted, and then when I cooled it back down, it would have tried to pull away from the other support. And actually would have been left in what's called a state of residual stress. There would have been a state of residual tension, because as it squeezed back, if it tries to squeeze back, then superposition would require that we pull it back to the other support. Does that make sense? In other words, if this gets squeezed so badly that it yields, then it's not going to bounce back to where it was before. So that when I cool it back down, it's going to want to bounce back and cool off to its yielded position, which is here. But it's rigidly affixed. So by superposition, I would then have to apply a tensile force in order to get it back to where it was. And that would be considered to be a state of residual tension. There'd be a residual stress, a leftover stress, because it had yielded along the way. Okay, so that's why I say it's important to check to see if this is going to be enough to make it yield. Okay, that's only a 70-degree temperature change, right? That's a pretty small temperature change, and yet even in that 70-degree temperature change, it's still got very close to a yield stress.
Does time have an effect? If so, say we kept it at 9.77 KSI for...
Yeah, but not that we're going to talk about it here. We'll talk about that in material science as well. Okay.
Just trying to jump too far.
once a day. Yeah, I gotta get it once a day.
Okay, let's real quick try to run through at least a little bit of 489. With a steel bar with the dimensions shown, determine the maximum axial force P that can be applied so as not to exceed an allowable tensile stress of 150 megapascal. So the allowed tensile stress is 150 megapascal. So what's the first thing you're going to do with this? And it's not a free body diagram. What's the first thing you're going to do with this problem? We have a thing that's got fillets and hole, fillets and a hole.
We could figure out what the stress concentrations are gonna be.
Right, so let's look at our W over H and our R over H. Or our, yeah, W over H, R over H, and 2R over H, or W, whatever.
2R over W.
Our ratios, all of our ratios, right? So, first thing you want to do is find your ratios. So we've got both fillets and holes, so let's start with the fillets. The things we care about for the fillet is R over H and W over H. What's R over H? What's R in the picture?
12.
Nope. We're looking at the fillets first.
Oh, the fillets.
What's R?
15.
15. What's H? 30. H is the narrow section. 0.5. So now we know we're on this line. 0.5 line. But we gotta know where we are on that line, so what else do we need to know? What else do we need to know? Can you see? Can you guys see this well enough?
It's a little small, but we should squint, we can see it.
I can teach you not to sit on that side of the room. Come over here. You got plenty. All right. So I got a whole bunch of little blue lines on here. How do I differentiate which blue line I'm supposed to use?
W over
W over H. Right. So what's W over H?
Go with 20 over 30.
What's W? Nope.
W is going to be 60.
W is the width of the thick section. 60. And H we already know is 30. So that's 2. So now I come in here and find my W over H equals 2 line, which is this one.
So, width.
Oh, this next side.
You see that? Can you guys see it well enough to? There's a WOH over equals 2, which is the third line down from the top. It intersects with R over H of 0.5 at a stress intensity factor of 1.4. So K for the fillet is 1.4. It's in your book, you can look it up later if you want to. Now let's look for the hole. So what are the values that I care about for the hole?
R and W.
Right, so I really only care about 2R over W. Now R was 15, so 2R is 30, and W is 60, so it's also 0.5. Right, so now I come over here, 0.5, come up, and it's 2.1. Oh no, sorry, 2R is not, it's a different R, sorry, my bad. It's not 30. What's R for that one? 24. Or no, 12, yeah, 2R is 24. So 24 over 60 is 0.4. So I want to come up to 0.4, come up to the axis, and that gives me a K value of 2.2. So K for the whole is 2.2. What's that?
These Ks have units?
No, because they're a ratio of dimensions.
Okay.
I mean, W and, no, they don't. They're just, sorry, ratio of stresses, not dimensions. Oh, it's not up there anymore. K was defined,
Oh, it's the average over the
max over the average, but yeah. Right, so it's a ratio of stresses, so it's just a unit's quantity. Okay? So, so can we tell yet? what the, is it gonna fail first in the hole or at the fillet? And we don't really know yet, actually.
We don't know yet.
Right, because remember, the fillet is comparing the stress, the sigma average used here for the fillet is the stress in the narrow section. Right? So I've got my sample, looks like this. Right? This section is sigma average for the fillet. This, the stress at this cross section is sigma average for the whole. Those are two different sigma averages. Right? So for the fillet, we're working off this section, for the hole, we're working off that section. So the hole has a larger stress concentration, but if the average stress here is smaller, it might still be more likely to fail down here in the fillet. Does that make sense? So we have to go back, we don't have time to do it now because we're out of time, but we have to go back and calculate the average stress in the fillet, you know, P divided by cross-sectional area. And the average stress here, P divided by this cross-sectional area, now reduced by 24. So the cross-sectional area here is now going to be, what, 36 times 20, the depth. And here, it's going to be 30 times 20. Now, it turns out the hole is still going to be the greater stress concentration, but.
And that's just a guess, right?
What's that?
You can really only guess or like try.
Well, I can, yeah, I've got the numbers in front of me, but 36 times 30 times 2.2, or I'm sorry, 2.2 divided by 36 by 30 times 30 is still going to be a larger number than 1.4 divided by 30 by 30, or 30 by 20. See what I'm saying? So that one's 1.5 times as big. This area is not 1.5 times as big. So I know the K factor is going to be the biggest one contributor. And for what it's worth, just so you have them in case you want to work through this on your own, P for the hole is equal to 49.1 kilonewtons, and P at the fillet is 64.3 kilonewtons. So, work this out in your own if you like. And that's it. We'll see you on Wednesday.
Great afternoon.
You too, Tom.
Hey Blake, are you going back to Sandy? Looks like you guys have a fun day of practice, eh?
Oh my gosh, yeah, it's gonna be great. Hoping for lightning so we can just go in and do a pool workout or something.
I guess I should turn this off before.